It's an honor to be back at my alma mater for the Design of Medical Device Conference 2012 to present to you what we believe is an exciting advancement in catheter technology, the adjustable stiffness. A brief historical perspective on the evolution of catheter technology. We begin with its early use in urinary tract intervention. The early Chinese used dried green onion stalks inserted through the urinary tract to access and drain the bladder. Later, solid metal catheters were shaped to more closely match either the male or female anatomy. A big advancement happened when the first rubber catheter was introduced by Newton in 1873. This same rubber urinary tract interventional catheter was by German physician Dr. Forssmann in a completely new frontier, the cardiovascular system. He went on to perform the first cardiac catheterization. He actually did it on himself. Like the early Egyptians, Greeks, and Romans, Dr. Judkins realized the importance of shaping the catheter. He took individual patient x-rays, then using a stainless steel wire shaped it to match the aortic anatomy, placed this shaped stainless steel wire inside a polyurethane catheter, placed the polyurethane catheter in a hot water bath. The polyurethane catheter took on the shape of the stainless steel wire. He inserted the polyurethane catheter through the femoral artery of the patient and was able to use the catheter to access coronary arteries. I think where we need to go now is an in vivo catheter that is shapeable. This idea or clinical need came about at a conference where engineers and physicians get an opportunity to interact. Dr. Sachar, an interventional cardiologist, approached us and said, I need a catheter that is soft to safely navigate the cerebral vasculature, yet, on a flip of a switch, becomes stiff to prevent catheter prolapse, which is movement of the catheter away from the target location during delivery of therapy. In this case, intracranial stenting. This clinical need was a very interesting engineering conundrum. Intracranial stenting is performed by Dr. Sachar to prevent strokes. Here are the people and dollar costs for strokes. Strokes may be due to rupture of cerebral arteriosclerosis. Cerebral arteriosclerosis can be medically managed through stenting. Stenting of the higher cerebral vasculature is still a technical challenge with current catheters. We need new technology to navigate this tortuous path and to reach the site for therapy delivery. We still rely on the interventionalist skills to read these ghostly 2D images, advance the catheter, and safely deploy the therapy at the target location. With current catheter technology, we have the ex vivo shapeable, where the distal tip can be shaped outside the patient, or the in vivo steerable. The ex vivo shapeable comes pre-shaped like these that can be chosen at the discretion of the interventionalist. If these do not meet their needs, the distal tip can be steam-shaped to various orientations. These series of images show the catheter tip loses its original orientation once inserted coaxially through a larger diameter catheter, and even more so once a wire is passed through and manipulated. With the in vivo steerable, you essentially have 4 subcategories, 2 of which have been reduced to clinical practice, the magnetic and pull wire. With the magnetic, there's an external magnet, when moved, controls the movement of the polarized distal tip of the catheter. The pull wire, like its name implies, deflects towards and away as it is pulled and released. The shape memory and hydraulically actuated catheter have not yet been reduced to clinical practice as far as I am aware. All these steerable distal tips catheters, as far as I'm aware, have the indication for use only for cardiac electrophysiology and not for cerebral vascular intervention. All these catheters require the interventionalist to physically push the catheter forward to advance the catheter. Most of importantly, none of these catheters has an adjustable stiffness material. It is important that the catheter is soft for advancement and on a flip of a switch become stiff for delivery. Here are a few approaches listed to adjust stiffness. Electromagnetorheological fluids have particles which, when large amounts of power are applied, can align, resulting in the fluid's apparent viscosity changing. It can go from a consistency of something like water to that of wet sand or gel. You can also chemically induce stiffness change by forming and breaking of hydrogen bonds. Biomimetic nanocomposites are a good example, and it's inspired from sea cucumbers. They are able to chemically change stiffness. You can also thermally induce stiffness change by melting and solidifying of wax and thermoplastics. We decided to choose thermal approach because it was easy, and with thermoplastics the process may be reversible. Here's a laundry list of thermoplastics in this case biocompatible polymers, all having low melting point or glass transition temperatures. The low temperature requirement was important because this material would be used in an interventional device, therefore we wanted to prevent thermal damage to the surroundings. We chose polycaprolactone, mainly because it's FDA approved and it's well characterized for its strength. It is used in sutures and tissue engineering scaffolds. Its thermal characteristics is well understood. So how do we make an adjustable stiffness device with PCL? Well, we built the heater right into the PCL. Here we show a schematic of the first embodiment of our device called adjustable stiffness film. It measures 2 cm by 5 cm with a thickness of approximately 500 microns. The cross section we show in yellow is the inactive PCL or solid PCL. This layer is sandwiched by a higher melting point polyimide shown in blue. We etch out a copper path, and when we connect a power supply, the current passes through the copper path. Through resistive heating of the copper, causes the inactive PCL to melt and become what we define as active. This short animation shows that in an inactive PCL going to active PCL when the current passes. Here we show the actual physical embodiment of the adjustable stiffness film. Now I'll play a short video that shows the adjustable stiffness film being able to support a 20-gram weight in the inactive state, and once the current is turned on, the PCL melts, the film softens, and it's no longer able to support the weight. This also shows the film able to retain the shape of the outer contour of a syringe. And as you can see, we're able to shape the film into various shapes and retain the shapes. So that was a film. And how do we make an adjustable stiffness tube? Well, we tried rolling the film, but it was not structurally sound. So we decided to make a tube. You need to start with a tube. We begin with a polyimide tube. Evaporate a thin film of gold, in this case acting as the conductive element. Deposit the PCL. And housed it inside a larger diameter polyimide tube measuring the following dimensions. And here you have the physical embodiment of the adjustable stiffness tubes. So we powered on the tube and did cantilever bending tests. Here we plotted force over displacement of 3 millimeters. As plotted, you can see the force decrease with increasing currents applied, and a very little difference from 200 and 250 milliamps. If we extract out the slope of these lines, you get a modulus, or Young's modulus. We can plot this over the currents applied. We get a sigmoidal distribution. There is a reduction of approximately 75% from the inactive state to an active state of 200 milliamps. We have shaded out the stiffness range of a few market catheters we measured, and they span approximately 20%. So based on this preliminary data, we worked with Surtech Medical to come up with our first catheter type. Here's the physical embodiment of our first catheter prototype. It has all the bells and whistles of a market catheter. In the proximal shaft, you have flush ports and therapy insertion sites. The midsection we call active, and this is where the PCL is deposited. With the catheter active, we can shape the catheter into a fairly complicated structure like this helical coil, and is able to retain the shape. The distal tip of the catheter, the radiopaque markers, and it's tapered and soft. So if we look at the cross-section of the active segment, we see we have an internal luminal diameter of approximately 7 French and an outer diameter of approximately 9 French. In red, we have the heating element, and above that, PCL in yellow is deposited. And the PCL is sandwiched between multiple layers of polymers. So we went forward and did some mechanical and thermal validation studies. Here we have a schematically shown our experimental setup. We have the power supply in green, which is controlled by the computer, and the power supply is connected to the catheter and activates the catheter. We record the surface temperatures. We applied cantilever bending similar to the tubes by controlling displacement, and we record the loads. Here we've plotted the thermal response of the catheter, temperature versus time. As you can see, the catheter rapidly equilibrates with its environment, and having a time constant of less than 30 seconds for all currents applied. Here we plotted force over displacement. The green trace represents the catheter in air at room temperature. The brown trace represents the catheter in physiological temperatures of 37 degrees C in a water bath. When the catheter is activated to get to a catheter surface temperature of approximately 40 degrees Celsius, we get approximately 15 to 20% reduction in force. If you remember, this spans the market catheter stiffness range. If we really juice up the catheter, get a surface temperature of 60 degrees C, you get approximately 60 to 70% reduction in force. Here we plotted stiffness over the range of currents applied, and you can see we get a similar sigmoidal type distribution like that for the adjustable stiffness tubes. There was approximately a 70% reduction in stiffness from inactive state to an active state of 300 milliamps. Once again, you see a 15% reduction similar to the market catheter range with 125 milliamps of current, which corresponds to a catheter surface temperature of 40 degrees Celsius. So where are we now? Well, we have a working prototype where we can get 15 to 20% reduction in stiffness, and this is comparable to market catheters. For future design modifications, as we anticipate for our second prototype, we want to improve thermal properties as well as range of stiffness. We're also exploring other polymers. Obviously, we also proceed with convective flow studies, which would affect catheter thermal response. We are also in line to do animal testing indicating the feasibility and safety of our catheters. With that, I'd like to acknowledge our group members and our funding source.